Hello. I'm going to bring Ross in here in just a moment. Thank you so much for joining. We are doing Immunology 101, a little nod to college, of course. So the 101 level of anything is the very fundamental basics of how our immune system works. So my friend, Dr. Ross Federman, whom many of you know from Tally Hall, has decided to join me, has taken me up on my offer. So I'm going to bring him in to be able to chat with us today about our immune systems and what we need to know. So I'm adding him here. Hi, everyone. Hi, back. So a lot of you probably don't know Ross as a doctor, as a PhD, I should say. Hello.
Hi.
How's it going?
Good, good. It's good to see you. You gave me the warning right away to put my do not disturb on, and I
Yes.
forgot to tell you that I can't actually put my do not disturb on.
Oh, okay.
So
So no one call you.
hopefully no one calls me. I'm gonna get a text at some point, at which point I need to quickly enter a takeout food order for someone to pick up. The order is ready to go. I just have to
I
hit
love
enter,
it.
but I have to know when it comes
Oh,
in.
yes, absolutely. I love it. That is probably the most 2020, 2021 reason for not putting on Do Not Disturb. I love it.
Yeah, so hopefully that's the only text I get. Although I
I
say
love it.
now, and I'm
Oh,
sure somebody's going to be tempted that I've already seen pop in
nobody
here.
will.
So I'm also going to try to turn my volume up a little bit to hear you.
Perfect.
Okay, cool.
Right
Sorry,
on.
I don't do this like casting here, especially off my phone often. So I'm trying to get situated.
Fair enough.
Yeah.
Well, like we were just dealing with earlier, Instagram lives have changed since the last time I was doing an Instagram live. So thank you for bearing with me.
Mm-hmm.
And first of all, thank you for saying yes to my ask of wanting to see if you were interested in doing an Instagram live so that folks can learn a little bit more about how our immune systems work, especially since we're in the middle of a pandemic. And I know a lot of people maybe don't know about your PhD. So first of all, if you know me in real life, anybody that's out there, and we've had any sort of conversation and I've said, oh, well, my good friend is an immunologist, let me see what he thinks about that. This is the good friend, the immunologist. So Ross and I met in 2009 when we were both living in Brooklyn. And I know Ross as Ross, the DJ and the drummer, and also Ross, the very curious scientific mind. So quick little intro. Ross was a Gruber Fellow and a National Science Foundation Graduate Research Fellow and holds a PhD in immunology from Yale University. He currently works in Boston as a research scientist. So welcome, my friend.
Yeah, thank you. Thanks for having me. And sorry it took a while to make this happen. We've been
No problem.
And if I look exhausted, it's just trying to buy a home in Boston is like the worst nightmare anyone can ever imagine. And it's drained all of my extra energy,
And
unfortunately.
you and your wife are both research scientists,
Yeah,
respectively.
yeah. And we've been both working to some extent on the COVID problem since it became the humongous, well, even before it became the humongous problem it is now and still to this point. But I should mention I'm not a coronavirus expert by any stretch of the imagination, and for a lot of the immune system I'm hardly an expert at all there as well. But I think for the 101 level, hopefully we can answer some questions.
That's awesome. I'm at a 101 level myself, so I love that. So guys, if you have any questions for Ross, if I would just invite you to use the question box rather than the comments, because the comments are going to get lost. So if anybody has any questions about our immune system and how it works, please feel free to ask. And as I'm sure you will agree with, Ross, a lot of experts will say, it depends when it comes to the answer to a question, and that's a very normal answer. Would you say that that's accurate?
Yeah, I think so. And I think one thing to remember is no one, we could talk about the immune system in a general sense,
Awesome.
but it is the product of a lot of genes, right? Which code for various proteins, which are all part of what create the immune system and what help define all the cells of the immune system and exactly how they behave and how they respond to things. And there are sort of prominent what we would call alleles or like isoforms of these components, but there are also different versions of them. And so you'll sort of, if it's a really small change, meaning like a single piece of DNA, like one little letter of the code, you'll often hear those referred to as like SNPs or single nucleotide polymorphisms. And that's sort of an extreme example of just the tiniest bit difference. But that little different thing can change all sorts of regulatory processes. And it really makes, so basically a long way of saying that no two immune systems are truly alike, especially since they also develop in response to a lot of environmental stimuli, things like your microbiota, the environment you're in. And so that really makes every immune system unique. So at a broad level, you can sort of define these general patterns, of course, but the depends answer is, oh, you're always going to reach a point where there will be a, well, it'll depend. And especially with coronavirus, it seems like we've really highlighted that in a way that everybody was kind of talking about all at the same time. Mm-hmm. People have different responses. You know, I had mono when I was 30. Was the first time I encountered Epstein-Barr virus. And so my bout with mono was probably a lot more intense than most people's.
Because of your unique immune system, right?
Yeah, just because the age, exactly, and the age that I had when I got it, but then you compound the age with certain probably things about my immune system or whatever I was doing at the time. And so, you know, that sort of different response to a lot of virus, it does exist, but you know, we're not always witnessing a brand new pathogen and seeing this entire sort of panoply of responses from different people all at the same time. And I think that was really highlighted throughout all of COVID and still is. Some people are long haulers and have symptoms months and months down the road. And you know, I think that really highlights sort of a lot of the different just the nuances in the architecture of one immune system to the next.
So I have a Bachelor of Arts degree in theater performance. Okay, fair enough. It's been many, many years since I was in an advanced biology class. And I barely made it through my advanced biology class. It was a lot of extra tutoring. And I know that there's a lot of folks that are either tuning into the live or potentially watching down the line that are in other time zones, that are maybe they're in junior high school or early college, or maybe it's been a really long time, like me, since I took a science class. It's never been the way that my mind has worked. And I've always really loved how passionate you are about science and of course how knowledgeable you are about science. So I want to be sure that we get to a couple of questions that are very much on the 101 level so that folks can have a couple of takeaways from this and feel like it's not too crazy, but it's also something palatable that they can share with friends and family. So I want to ask you the first question that came through to me a couple of weeks ago when I put out on my Instagram stories, hey, I'm doing a live at some point. Does anybody have a question about about their immune system? So here's the first one. And that is, how does your immune system learn and remember how to generate certain antigens?
Okay, so one language correction there that I'll quickly jump in and just
please.
Clarify. Yeah, so
correct me all the time.
The term antigen refers to the target of the immune system. So normally you would refer to the antigen as being part of virus or bacteria. I mean, it can also be a self-protein in the case of autoimmunity, but that's a a sort of a different story. But really, antigen is the equivalent of a target. So that's sort of what antibodies target. For example, they target a specific antigen. And so maybe the term you're looking for is antibodies, and how does the immune system make these proteins that are able to bind to any number of antigens?
Because we hear the word antibody thrown around a whole lot.
Yeah, no, and it's funny because even people who, you know, I think there are some great science communicators, and for a couple months, I would hear Sanjay Gupta, who's on CNN, who I think is a good example of that, also a University of Michigan guy. So
go blue.
Yeah, I think we won the game, but it didn't end yet. So I actually shouldn't. The other team was I'm checking the score. Okay, up by 15, a minute and a half left. So I think we're doing okay. It's
Okay.
been a follow to the first round, but yeah. So he at some point was referring to antibodies as cells, and I thought that was a bit that to me is something I was surprised to hear that mistake being made. Just going to call him on that. So, if you go way back to sort of the most basic level of biology. There's probably, what you could consider the simplest component of life is a cell. And so we are multicellular organisms, meaning we have millions or billions of cells in us that sort of come together to create who we are. And some of them are skin cells, some of them are muscle cells, and some of them are immune cells. And you could still have a cell that's its own full life force, like a bacteria or yeast or something along those lines. But then within cells are proteins, and proteins are essentially either structural components of those cells, or they're what we call enzymes, which are like protein machines that do something really specific. And a lot of those machines make the other components of a cell. They make more DNA, for example. They make the lipids that surround the cell. So, the cell is sort of the simplest form of what you'd consider like autonomous life, but at the core of it, it's all the proteins that make that cell up or make all the other things in that cell that are really doing the heavy lifting, I think. And proteins are that's essentially what your DNA codes for. So when you talk about genes, like each gene will make a protein is the simple way to look at it. And so some of those proteins, the proteins in our immune system, have evolved to be really good at recognizing dangerous things, whether it's a virus or a bacteria, or even sort of just noxious stimuli, some types of toxins and things that would be harmful to your cells and to your body. And there are two major categories of that detection. There are what are known as pattern recognition receptors, which they basically discover really broad families of structures. And they could say, you know what, whenever I see that, I only see that on bacteria. I've never ever once witnessed or encountered a form of life that exists that has this specific thing in it that's not bacteria and we should protect against, right? And then on the other side, you have incredibly specific protein receptors that can become antibodies, for example, that recognize like exactly that particular strain of a virus or a bacteria. And it's actually not even really just that whole thing. It's that it recognizes an antigen, which is just some little piece of some component of that particular pathogen. And there are, I'm afraid to get into the details of how we make antibodies, although I know my friend Helen's on, I saw her come on, whose her thesis is in this area, so she could speak to it a lot better than me. But
we can do this again.
But I will mention there's a really cool protein called RAG. It's like two proteins actually that form a complex called RAG1 and RAG2. And those really go into your DNA and make all sorts of random changes to allow our bodies to sort of experiment with a whole bunch of unique versions of antibodies. So constantly our B cells, which are the cells in our body that can do that type of gene rearrangement, or at least they're the ones that can do it controllably and accurately, right? That are sort of our bodies allowed to do this. They can create just millions of different antibodies that are all unique, and we can kind of try them out constantly. Your body's always doing this. And if it attaches to something in the right context, that's what your immune system would say, okay, we can detect this thing, and while we're detecting it, we're getting a lot of this other damage going on over here, and we're recognizing a lot of those primary components that we only see on a pathogen. So we're going to put 2 and 2 together and figure out that we need to take this random protein that we made, because now we know it attaches to something very dangerous, and we are going to make a lot of these. And that's how you create antibodies. And so then those go into your blood and they float around and they continue to protect you. And so sometimes you can either
like Pac-Man, right?
Well, I would say something like
I'm aging myself, I know.
So there are cells called phagocytes like a dendritic cell, for example, is one of those. Neutrophils can do this, macrophages. These are all random cells in your body, which are sort of like Pac-Man. I mean, phagocyte basically means a cell that eats. And so those, when their receptors detect, attach to something foreign, they literally will engulf it and break it down. And that also helps the process of teaching the rest of the immune system to recognize the bits and pieces of it that it takes in and presents. And that's its own whole area of immunology that we could talk about that's really fascinating too. But that is a key part of the process of figuring out when this random experimentation is actually helpful to you or not. Yeah.
Right. So to that point, really quick, what got you into immunology? That was another question that came in.
Yeah, no, it's a fair question. So when I left school to join the band, I was planning on going to med school. So I was pre-med, so I was sort of by default in these biology classes. And I mean, I was interested in biology, but at some point I really thought, I wanted to be a doctor. And I sort of, through the years in the band, I think I learned more about what science really is and what medicine really is. And I realized medicine is not a science, really. It's like I mean, there's medical science, but we refer to medicine as a practice, and it really is a different approach. It's medicine comes from a place of, help people any way we can, whenever we need to. And we may not always know exactly how or why what we're doing yet is working, but it's just we try it. Let's whatever it takes. And as a scientist, the sort of the primer of it is more, let's learn exactly how this works, and it may take time. It might take all the time in the world, and it's going to take a number of different approaches and a lot of creativity from different people to try to sort of find ways of asking these questions. And eventually we will create a model that explains exactly how this works, and we'll continue to amend that model and our understanding of it based on new data that we collect. But it's a bit more of like a discovery and investigation kind of thing. And I think that just really started interesting me more than, I don't want to say it interested me more than helping people, but I think there's some, there's like, to me, like I feel like we'll help a lot of people with all the knowledge that we gain. And
Sure.
So I think I'm just more driven to be sort of the detective, maybe, as someone, the sort of like.
Well, it seems like there's a lot of creative thinking, even though they're two very different fields. There's a lot of creative thinking that goes into solving problems in the science world, just like there's creative thinking that goes into putting together 5 creative minds to create music.
Yeah. No, it's funny. And actually, when I joined my PhD lab, my thesis advisor, one of the first things he said to me was, you strike me as somebody who's a little more on the creative side, and let me tell you about this other. So I went to inquire about, we do these rotations in grad school where you would spend a couple months in a few different labs and try to.
And remind us how long your graduate program is. I feel like a lot of folks don't realize how long science.
Yeah, it's generally 5 to 6 years. I think when I joined, the average was 5.5. That always changes and is highly. Here's another. It really depends. It is highly dependent on the nature of your research, your advisor, and what they think, what they consider to be sufficient work, a body of work to defend as a thesis. Most programs, if they don't have a requirement to publish in a peer-reviewed scientific journal, certainly really encourage it, and generally won't really want you to graduate without having at least been a part of that process. So, and that's something that some people in their third year of grad school publish in Cell or Nature or Science and get these huge blockbuster papers, and that's just how well it goes for them. And
right.
So I mean, it can go up to 8 for some people. No, I mean, it really depends on what you're working on, where you're working on it, and I think in the cases that it really goes on to 8 or 9 years or something, there's some desire from the person doing the research to really finish it up. But yeah, no, it was mine was 6 years, so I was there for 6 years, and so. But yeah, getting back, the rotations basically make up the first half a year to a year of it to just kind of figure out where you're going to be at home. And I had seen my advisor present on actually some more virology kind of traditional studying how viruses get into cells. but when I went to talk to him and we talked a little bit about my music background, he sort of introduced me to this much more creative project, which is what I ended up working on, which is really kind of off the beaten path. It's really not, it's like hardly immunology at all. And I'm kind of grateful that the department allowed me to just stay in the immuno department working on such a sort of off-kilter research thesis. But it was good because to me, a lot of, I'm most interested in how biology works in the ways in which it influences our immune response. And, for me, I guess I don't. It's easy. It's easy to say it's easy to say how to feel like oh no.
Is the food here?
No, I think my order may have timed out.
No,
anyway, it's okay. It's okay. I think we'll be okay. So I may just have to have a longer pause if this has to go through during it. But no, I don't want to. It's weird to say now looking back that I saw this coming. Because I think a lot of people would say that, but I can assure you, if we looked back on my letters for admissions, where I was basically explaining to programs what was driving me to apply there, to me, immunology is for it's still it's an old field, but like the true molecular revolution in immunology that happened just over the last few decades. You really opened up a lot of doors to really understand it better. And I think, we were still doing a lot of research in mice as immunologists, and we still are, but a lot of the tools to study the human immune response more specifically have gotten a lot better. Things like, I'll just throw around some terms that aren't going to mean much, but there are these things like single RNA or single cell RNA sequence analysis, and really these larger scale microbiome sort of what we refer to as 26 RNA sequencing or gut microbiome profiling. And there have been, technology has allowed us to learn a lot more. It's like a really exciting time basically to study the immune system.
It is.
So putting these together, I thought, well, why not, jump into a field that I know is relevant and always will be. People are populating parts of the world that we didn't populate before, and that will drive interactions between humans and nature really quickly over a 10 to 20, 30 year span of time. And our immune systems really have been evolving over hundreds and hundreds, if not way longer time scales than that. So it sort of made sense that pretty soon we were going to need people who could understand these new challenges to our immune system and try to find ways to make vaccines against them. I was always very, very drawn to the story of the vaccine and the polio vaccine race, and also to the story of the 1918 pandemic, and even things like when something like Ebola surfaces, and sort of try to learn about this.
Zika.
These entities that basically bring mankind down to our knees at points throughout our history when we feel invincible. And then these are things we can't even see with the naked eye. We didn't even really have a good handle on what viruses were until just about a century ago through the 1980s. It's
incredible.
Yeah, and the sad thing is how much we sort of I feel like we squandered a lot of that knowledge in the response we had to the virus, because we're right back where we were in 1918 with a global pandemic. That's just kind of.
Because our leadership matters and our words matter and science matters because it's real. I want to get through a couple of questions, but for folks that are just popping on or wondering what this is or what have you, just a quick recap. A lot of you, of course, know Ross from his contributions to Tally Hall, which is awesome. But he has a whole other life in the regard that he is actually a scientist for real, which is why I asked if we could have this chat today. So Ross was a Gruber Fellow and a National Science Foundation Graduate Research Fellow, and holds a PhD in immunology from Yale University. And he currently works in Boston as a research scientist. So definitely more than your favorite drummer from your favorite band. Not that there's anything wrong with being a drummer in a band. We met back in 2009 when we were both living in Brooklyn. And I can attest that when you were in between parts of your recording cycle or your touring cycle, you really were reading scientific articles, looking at textbooks, keeping your brain sharp for when you were going to go back to school to pursue this. I remember that from way back. So wanted to point that out as well. So
actually, real quick, did we ever did you come to any of the Brooklyn Secret Science shows?
No, I think that was right before we met, unfortunately.
Maybe. So those were another place where I began to get really interested, because they would have academic PIs come and just give,
Oh,
you know,
cool.
talks, like very basic level talks. And some of them were really fascinating. And I sort of like, I was drawn into the world of like research science through that to some extent. And it's right around when the TED Talk, there was like a time when TED Talks just exploded in popularity. Right?
Kind of like podcasts now.
Yeah, exactly. Yeah, podcasts are. I don't know how anyone can find. I've just been chipping away at like a 90-minute podcast over the entire last week, and it's like, how does anyone find time anyway?
I love them, but I've even had very good friends start podcasts in the last 18 months, and I am the worst at listening to them, and I love them, but it's hard. There's some really great ones too. Okay, so you guys have had some really, really awesome questions. It's going to be impossible for us to go through them all. I'm just going to warn you in advance. I'm sorry, we're only going to be able to do this for an hour. That's only how long that it saves on Instagram. It's going to cut us off after an hour. So I do have to be mindful of the time.
Okay,
but
I'll try to answer questions more quickly.
Yeah, we can even do like a lightning round.
Yeah.
Although it's science, so it's hard to do a lightning round with science.
Yeah, I'll just say it depends a bunch of times in a row.
I like that. I like that. So, okay, so quick and hopefully innocuous question. What's the deal with over-the-counter vitamins? Do they help, or is there a better way regarding our immune system?
Yeah, I mean, there's definitely a better way. I would say wearing a mask is probably going to be a better way to protect yourself than taking vitamins. I would say getting a vaccine is absolutely going to be a much better way to protect yourself than taking vitamins.
We have a few questions in the queue, by the way.
Yeah, okay. I would say certainly all the things that, I from what I've heard, there is some data that said vitamin D could be really beneficial. I don't know if it's that a lot of extra vitamin D necessarily offers you more protection, as much as it sounded like if you had a deficiency in vitamin D, that led to sort of worse outcomes. So I would just say, and this is all consistent with the fact that your immune system needs vitamins and nutrients to function. So I would just make sure you're eating as healthy as you can be. Whether it's, if you feel like you need to take some, I take a supplemental vitamin because some days I don't have the time to cook the meal I want to cook, and I just like to make sure that that's there. But the best thing you can be doing is eating healthy and staying well nourished.
I have not had a cold or the flu in a very, very long time. And I attribute that to extra sleep with this pandemic and wearing a mask. I don't know if anybody else has had that experience.
Yeah, I mean, certainly, I think respiratory viruses are down all across the board, which makes sense. They're all spread the same way. So
amazing, amazing. So quick history science question. What potential disease/virus are on the verge of eradication? Anything?
I don't know. I mean, I think polio is not really eradicated yet. So I think that's something people are still working on. I think really smallpox might be the only thing we've actually fully, completely eradicated.
And why is that eradicated?
Sorry?
Why has that been eradicated?
I'm not sure why that was a lot more effective, like the campaign to pull that off than some others. Even things like polio that we've done really a great job of, at least in our country. But the thing is, it ends up being really specific to what part of the world you're in. So it's hard to find examples where it's like a really clear, we can get this off the map period. It's very, very difficult to do that, as you can imagine.
Right.
Controlling it is the best thing we can do, and that's where a good vaccine really comes into play. I mean, when you have people, like, any vaccine's only as good as enough people taking it, frankly.
Exactly.
And so we're sort of running into low vaccination numbers now in terms of. We're clearly not to the end. There's still a lot of people who would like to get vaccinated for coronavirus that haven't had a chance to yet.
Right.
And I encourage everybody to, obviously. But just based on polling, it sounds like there are enough of the people in this country who are not willing to take it that it's not going to, it's not like everybody just, like, the vaccinations are just going to end this right away by any stretch of the imagination. If the numbers that people are reporting in polls right now are the actual numbers we end up with for vaccinated people, I'm afraid.
I'm sure a nightmare for you, given your position. You taught me something very interesting a few years ago. That I've shared with a few people that also didn't know this. There is a way to check whether or not the vaccines that you received as a child or have dropped out or not, or are still efficacious by, and obviously you're going to correct me if I have any of this incorrectly, by running just a routine blood screen to check the titers. And I did that. I work primarily in Southeast Asia. I had been living in Indonesia until last March when the pandemic really took off. And it was advised that I get a booster for both polio and measles, because there were certain pockets of Indonesia where those diseases were still very much widespread. And so even though I had like good enough immunity from my childhood vaccines, it was suggested to me by my doctor that I booster. So could you potentially talk about titers?
Yeah, and I'll also mention, for anyone who may be either pregnant or thinking about becoming, it actually has been recommended to get a booster while pregnant for certain vaccines, because when then you'll get sort of the boost of new antibodies, and you can pass those on and provide that immunity to the fetus. And so that, and it's like newborns don't necessarily start making their own antibodies right away. They get a lot of them sort of from their mother that for a little bit to kind of get them into the phase where they can really make their own antibodies. So sometimes it's important for certain things like measles that can be really potentially deadly for a newborn baby to try to get as many of those antibodies from the mother. For different vaccines, I mean, really, and again, keep in mind that vaccines are designed to be a better version of the natural immunity you get. But even with natural infection or vaccines, the longer, like the time span with which you retain good enough, high enough titers of those antibodies to have the effect you want them to have to be protective, you may need boosters at certain times, and it's different for every virus, it's different for every vaccine. But to your point, yes, you can actually check for that. You can ask your doctor to titer get a titer for specific vaccines. Do I still have these protective antibodies? Now, one thing to keep in mind is antibodies are not the only player in the immune system that protects you. You have what are known as memory B cells, which may not be making a lot of antibodies at the moment, but they have a little imprint of the antibody design. And if they detect that again, they're going to just crank on the antibody making, waterworks once again. And so you also have T cells that are a big part of your response, which I did, to get into the specifics of how those work is another whole thing.
That's another lot.
But akin to B cells, they work at a cellular level as opposed to facilitating a process that works at the protein level. But they're also very specific to certain pathogens and things. And you'll also have memory cells of that type. And so these cells basically hang out in your body. And like I said, they already have their specifically kind of rearranged and redesigned architecture for specific recognition. So even if your antibody titers are down, it doesn't necessarily mean your next response to this pathogen is going to be as bad as it would be had you not have been vaccinated. But it may not be the immediately protective response you'd want to see having good antibody titers.
I see. I like it. So here's some good questions that are coming in here.
Yeah, it's getting into good stuff.
I wanna ask. I don't know. I think I hit a button. Anyway, sorry, Instagram. I wanted to ask you as well, let's see. Oh, I'm recalling a conversation that you and I had in very late February last year when I was still living in Indonesia. And you were sharing with me, this is like right before I think it was declared a pandemic, and you were urging me to come home. You had shared that there were some companies out there that had been working on mRNA vaccinations for other diseases. This is before COVID, and that they had been working on these platforms for upwards of a decade. Can you comment a little bit if there's anybody listening that's maybe hesitant to receive either the Mrna or the Pfizer vaccine because of some incorrect information that's out there? Oh, we don't, oh, it's too new, whatever folks are talking about. Would you be able to comment a little bit? I know that's not exactly what you work on, but
but I think I think it's important to try to break down these concepts as much as we can to explain, because they are the Pfizer and Moderna mRNA vaccines are new technology. As far as I know, these are really the first ever approved, not even just vaccines, but mRNA therapies. Now, that's something that conceptually has been in a trial for a while. And earlier we talked about how genes code for proteins, but there is one intermediate step between the DNA gene and the protein, and that is something called messenger RNA. And that's just a copy of the gene. So you want to protect the actual DNA gene as much as possible. So we keep that in our nucleus and we make sure nothing happens to it. And if that starts changing too much, we call those changes, by the way, mutations. So if you start accumulating these mutations in your DNA, that becomes very, very problematic and is sort of your fastest route towards having a cell become cancerous and really become a major problem. And so our cells have evolved to really protect the DNA, and the protein stuff, that's all happening outside of the nucleus, and you basically make a copy of it on RNA, or messenger RNA, and that mRNA goes out of the nucleus into the rest of the cell, and it makes all the proteins. And so these vaccines are basically saying, okay, let's, well, I guess before we even get to the vaccines, what mRNA therapy was designed to do was to say, okay, well, if our body isn't making the right protein or something like that, or maybe there is a mutation, we don't want that anymore, let's put in the correct mRNA and just deliver that to the cell and it'll make it. And as far as I know, the issues that they've had with those over the years is that it kept eliciting an immune response because there's all this foreign, and it's not, I shouldn't say foreign RNA, you know, RNA is the same for the RNA at its core, like the sequence of it will be different, but it's not like the actual molecules that make that RNA are any different in any type of person from being to being. So people might say, like, I've heard monkey DNA coined, like a term thrown around, and like monkey DNA is actually really the same as human DNA, and it's the same as like bacterial DNA even, or viral DNA. The difference is what that DNA codes for, the precise sequence of all of the letters in the DNA and the proteins that they make. But so what would happen is that mRNA, maybe just the way it was delivered, probably the way that they had to package, you know, because you can't just like RNA is it's a tiny, they're long strings of this. It's a molecule that you can't just handle like in a tube or something and sort of stick it in somebody. It has to be packaged in a more stable environment or some type of little delivery mechanism, and that's, you know, they make these particles that are you know, kind of represent almost like little viruses or cells or bacteria in some way, and they can hold all of that RNA and deliver it to your cell. But from what I understand, that process sort of elicited an immune response because your body was just reacting to this sort of influx of RNA coming, you know, because it sort of resembles like a virus delivering its genetic material into your cell. And, you know, I think in a sort of when life gives you lemons kind of way, people realize, well, what if these were vaccines, then we would want an immune response. We would want whatever this RNA codes for to be something that our immune system thought was foreign and detected against. So that all kind of got turned around, and people were actually working on it to make cancer vaccines for a while to allow your immune system to sort of recognize and destroy some specific cancerous mutated protein that you would deliver. But the main advantage that it has is it's fast. Like the platform to try to just put it together, it's fast because we can do the research to sequence the RNA, the viral RNA, and figure out what we need to deliver pretty quickly. Whereas, which is traditionally, vaccine design can be a lot of trial and error. It can take years and years and years. Oftentimes it's what we call like attenuated virus, which means that they basically just pass the virus through all the infecting from different animal to different animal to try to isolate a version of it that elicits an immune response but doesn't make you as sick. And sometimes you actually take the virus and you just like destroy it through heat or other chemical disruption, and you just kind of shove that into somebody, and it's like enough of the pieces of the virus still exist in this mangled, destroyed format. It's like, you know, if somebody just, you can imagine it as like, if you want to recognize, you're not allowed to go into somebody's like art studio and see any of their art or anything like that. And that's what you'd want to do to sort of like be able to recognize it. The equivalent of like some vaccines is like, just take all of the art and the crap and like tear it into pieces and like throw it into trash bags and prevent it from actually being the effective art it was. But if somebody was to rummage through that trash, they'd be like, all right, here's this little watercolor section. So if I ever see this, I know it was part of the art that I couldn't see the whole thing of, maybe because it was like too dangerous to see it all in this context, right? So, but that's a lot more trial and error, whereas this mRNA approach can be a very directed thing. And yeah, it's different, but you know, at the end of the day, RNA is by nature a very transient molecule. And so, you know, there's less, with a virus, it's going to, the same RNA will be there whether the virus delivered it to you or the vaccine delivered it to you. So if you get sick, you're going to get all that same RNA. The only difference is you're going to get a lot of other RNA with it, and that RNA is going to make a lot of other proteins with it. And those proteins are going to allow your cells to make more and more and more virus and really infect your whole body and make you very sick. Whereas in this case, same RNA goes in, but you remove all of the pieces that would allow it to replicate or cause an infection, yet your immune system can kind of recognize the shape of it nonetheless. So it's a really elegant way. It's sort of telling our cells, like, make the protein, have it on the surface, which is what would happen if a virus infected it. The same protein would be all over the surface. So your body really thinks that it's there because you're infected, when it's there because you just took a small dose and sort of directed your cells to make it.
I love it. So we've had a couple of questions come in about how does the immune system react to a vaccine. So there you have it. A quick question is, have you guys gotten the vaccine? And do you recommend that people get the vaccine when they are eligible? I received my first dose this week. My arm hurt for 3 days. It still kind of hurts. But as you've already said, Ross, that's very, very normal immune response. And I look forward to getting my second. What about you?
Yeah, I have not been able to up until this point, but I have an appointment to get mine on Tuesday in a few days.
Love it.
I'll be getting the Moderna mRNA vaccine. I would have also received, taken the Pfizer if that was offered, and and Johnson if that's what was offered. So yeah, very much so looking forward to that. And I've been a lot of the, my company that I'm at, we really considered our work on this to be important enough that we didn't want to just stop lab operations and stop in-person work. So we've been going and being as careful as possible. But having been going in to continue this research, throughout the entire last year, it's nice to finally feel like I can access some additional protection for it.
That's wonderful.
Yeah, and I would say I'm looking forward to the first. I'm not necessarily so much so looking forward to the second dose.
But we're still going to do it because it's important. Of
course, yeah. And I think, to mention that, a lot of the vaccines that we have that have been developed over decades and decades and decades,
right.
people have been able to tweak them and find that, that point at which they offer all the protection you need and you never feel a thing, right? But with these, it sounds like you're going to feel a little bit that they're working. And I think maybe I don't think anybody should be sort of dissuaded from receiving the vaccine because of that. Because really what it is it's a sign that your immune system is reacting to it.
Exactly.
And that's good. That's what you want to have happen. And again, in an ideal case, normally vaccines do that without you ever knowing about it.
Right.
But this was very much so an approach of, we're going to shoot for, we're not going to try to come in low and have to increase what we're doing in order to get that response. It was much more of a, like, let's hit the head of the thing, over the head with a hammer and really do everything we can to get the best response possible. So I think as a result of that, we're seeing vaccines that have a little bit more side effects than your average vaccine. But, in some ways that was by design to just find an answer quickly and an effective answer quickly. So I think that's where we're at.
And build on all of this incredible knowledge that we have. I mean, we didn't just pull this out of the sky one day. This is off of decades and decades and decades of knowledge. I think that's important for people to remember.
Yeah, very, very, very much so. I mean, all science as we know it, whether it be immunology, vaccinology, virology, or even molecular biology, I mean, it's all, very, very building on, centuries of people making observations and documenting them.
It's a wonderful time to be alive. I say that in all honesty. I have to be mindful of the time, Dr. Federman. We have about 14 minutes until Instagram cuts us off. I want to switch gears a little bit with some of the questions.
Sure.
Let's try to keep this one short because it's not COVID related. What advice would you give to those just getting into the immunology or science field? And with that, is there something you wish you would have known prior to getting into the field?
No, I don't think so. I think it's about what I expected. I would say it depends, you know, it depends on where you're at in your career. So I would always advise people to reach out and talk to, whether it just be through email exchanges or a phone call or some way, you know, find somebody who can really talk to you about sort of what the process entails, maybe at the next step. So if you're in high school and you're really thinking about going into it and doing some research, find an undergraduate, maybe a family friend or anybody you can, or even, you know, you could always email professors at a school nearby or something, and even just say, hey, I'd really love to talk to some undergrads there who are studying science and see what's that like. And if you're an undergrad doing research, you know, make friends with some of the grad students in the department and talk to them about what grad school's like. And as a grad student, I talk to people in either industry or doing postdocs or professor. You know, you always want to just sort of gather that information. And so I would just try to find somebody that can kind of share that experience and let you know really what it entails. But, you know, I think it's one of those things where you really have to be curious. And I'd say if you're not curious, you're not going to be driven to want to put in the work, because it can't, especially, it depends though, again, just going into science as an undergrad is, you know, and then sort of like doing a little bit of research for credit is a little bit different than going and embarking on a PhD thesis. Right. And spending half a decade really digging deep into one really particular area. But so, you know, but
it's obvious you love it.
If you're the type of person who's very curious and every time you get an answer you still want to know more, that's a good sign. And I would say, you know, you could expect to continue and find the right resources to help you answer those questions, which isn't always easy, but they're there somewhere.
I love it. Real quick, I may even be able to answer this, but again, you'll jump in if I'm incorrect. What's wrong with the second dose? Nothing is wrong with the second dose. It's just how your body's immune response is to that second dose. What else?
It's just something that we would refer to it almost like a prime, you know, and then a boost. Like it's the same thing as like a booster, right? It's just saying like, you know, there are different phases. I would pull out a book, but that I have sitting on the coffee table at the moment. But to find the figure and then hold it up to the thing would be. But you know, if you look at sort of the number of antibodies your body makes, there's the infection or initial vaccination, and then certain number of cells and a certain timeline, and when you hit certain numbers of antibodies and memory cells and all those things. It just so happens that if you provide another dose, you really boost that up a lot, and so that's why a lot of vaccines are actually multiple doses, even vaccines that we've had around for a long time. The reason I was not so looking forward to it is because that's generally the dose that you're going to feel the effects of it from everything I've heard about these mRNA vaccines, which is consistent with, you know, in research, if you were, you know, basically, I think the key thing to keep in mind is the sort of the 101 part of this is when you feel sick, you're feeling your body's immune system responding to whatever that you're sick with. And
man, so, I wish the vaccine was drinkable. I just happened to catch that comment. That would be so much easier. But that is just not how this works, sadly.
No, not in this case. Although people have been working on oral vaccines. Those are being researched, probably primarily for pathogens that would be gut pathogens, right? That you would normally encounter in that particular place.
That makes a lot of sense. Is full eradication of the COVID-19 virus a pipe dream, or are we entering an era of persistent boosters?
We're definitely
10 minutes.
I'm almost positive we're going to be entering an era with persistent boosters. So as far as getting rid of it altogether, I can't imagine that's going to happen all that soon at this point. Keep in mind, most of influenza as we know it is all sort of downstream effects of the 1918 pandemic. And so that just happens when a virus like this gets a foothold, you know. It can really stick around for a long time and mutate and keep evading the immune system. And you know, the one thing to keep in mind, I guess, on the sunnier side of that is that while coronavirus is an RNA virus, meaning, again, when I said RNA is by nature a little bit more transient, it's less stable, so it's more prone to mutations. But it at least is not a segmented genome, which is the case for influenza. So influenza has the ability to sort of mix and match in ways where you might hear of like H1N1, and then all of a sudden it's like H1N9, and you're like, these are actually different genes, different genes coming together to form a new virus, really like a new influenza. So that kind of shuffling doesn't really happen as much in coronavirus, but it does still mutate quickly. So it will be sort of a race against time. And I think if we can get our vaccination numbers up enough, it's possible that we can really quell this thing, but it's going to take a long time. It would be my guess.
Can we still get COVID after receiving the vaccine? And do we need to still wear masks in public?
Yeah, I certainly would. Yeah, absolutely keep your mask on for a while until we better understand the efficacy of the vaccines against these variants. Certain variants have what are even known, I think the New York variant, there is like a New York homegrown variant there now that's very alarming. It has, I think it's like the E something K mutation, or I don't remember the exact mutation, but there are a couple. I'm almost positive it's the same mutation that the Brazilian strain has, which is actually referred to as an escape mutation, which means the one thing that mutation's good for is taking most of the antibodies that used to recognize the virus and causing them to no longer recognize the virus. So when that happens, that makes it a lot harder to try to get rid of. But keep in mind, our antibody response is what's known as polyclonal, which means it's in many different antibodies. And so even if some of the antibodies that you create don't necessarily recognize a variant, you're probably still going to have some that do. And then it's a question of, well, how good at neutralizing the virus are those? Because you get a whole bunch of antibodies that you make, and some of them are going to be more effective than others at different pieces and different mutations. And that's another thing to keep in mind is everybody's response to the vaccine is unique. So while we're all getting the same vaccine, the actual antibodies that you create to it will absolutely be different than the person next to you and the person next to them and the person next to them. And so here's another depends answer, right? Going back.
Yeah, there's so many.
But you'll be more protected, certainly. So absolutely get the vaccine, but no, don't assume that, by being vaccinated, you've got a total silver bullet for protection. I'd say, really, if you're with other vaccinated people, and no one has any reason to think they encountered somebody sick or may have, sort of be harboring this one of the variants or something like that. But it does sound like the vaccines are particularly good at least the mRNA vaccines are particularly good at blocking spread of the virus as well as just sickness from it. So, that's promising. But I would definitely wear a mask until we know a little bit more about kind of how the variants are going to affect our vaccine. Yeah.
You said something really great to me at some point in this past year. I don't know, you and I talk a lot about this. You said to treat every test, every vaccination, every case, everything as a little data piece, because we're studying so much data to try to figure out how everything works and to ascertain patterns and to understand everything a bit better. So somebody else had commented like, oh, my first vaccine, I had bad side effects. I'm paraphrasing because we're running out of time. So what would you say to that?
Oh, yeah. So, right. Some people are having kind of the second dose response upon getting their first dose. Now, anecdotally, I have heard this happen to a number of people who recently had COVID. So it's like you actually getting the infection, might have been worse still or not, but felt maybe like that first vaccine dose would. But then when you actually get the first dose of the vaccine, it's sort of like a boost to your immune response. And so you're getting that feeling. And yeah, it does sound like that again, anecdotal. There might actually be studies out now about that because I have heard people beginning to mention that we might, to kind of be more efficient with vaccinating if you still have like titers for coronavirus,
right,
and it's obvious that you had a recent infection that you still have antibodies to, you might only need that one dose of the vaccine to basically be fully have your immunology or immune response fully boosted there.
Yep. I will be saving this live for the person that asked. Hopefully, I'll definitely save it to my grid for IGTV. It should allow Ross to save it as well, but we will figure that out so that this stays evergreen for sure. Ross, we're on the last 5 minutes. Any other parting questions, comments, anything that you want to share? I don't know if we're going to get to another question from the group.
Okay. No, I don't know. I guess, yeah, hopefully.
What do you love about your job?
Oh, what do I love about my job? My job is like a dream job as far as I'm concerned.
So great.
Yeah, I did a lot of work in grad school trying to figure out what the rules are behind protein function and
Mhm.
structure and how, putting different, so proteins are all made up of amino acids. There are 20 different amino acids, just like there are like 26 letters of the alphabet. And when you put them in different patterns or order, you'll get different words and sentences and paragraphs. And so that's precisely um, how our proteins work. And the difficult part about studying that process in detail is that most proteins are like 300 amino acids long. So 20 times 20, 300 times, or 20 to the 300th is a number larger than there are total atoms in the universe. So even just a perfectly average size protein, there are more possibilities of that perfectly average size protein than atoms in the universe. So there's no way we could possibly comprehend every single iteration of that and what it means for what that protein does.
Mhm.
And ideally, if we knew that, though, because I started off with the fact that proteins really do everything, we could do anything we want in medicine. And so what my company is trying to work on is basically applying a lot of machine learning and sort of just computational algorithms to better understand the interaction between those crazy sentences, those
Awesome.
orders of words. Basically, just like by reading a lot of books would be the equivalent. Like if you just throw words on a page, it's not going to make any sense. But if you read every book in the world, eventually you'll be able to throw the words on the page to know exactly what to do. So that's what my company is working on. It's called Generate Biomedicines. We're not very public yet. It's still a pretty like early stage biotech company, but hopefully we'll have more to share about all that stuff soon. We do have a publication coming out shortly about our work with COVID as part of a Gates Foundation consortium thing. So
Oh, that's awesome.
try to post that when it comes out. It will be behind a very expensive paywall, I'm sure, but people can at least access the abstract and kind of
Sure.
get a sense of what we did. Yeah.
Love it. So thank you again so much for wanting to do this. And there have been a couple of comments asking for more. So I know you are exceptionally busy, you and your wife working in your respective labs and also trying to buy a home. So
Yeah, the home part of it, man. So
it's a time suck, I would imagine.
it's insane.
Wonderful, privileged problems, but still a real time suck.
Yeah, for sure.
So hopefully we can do this again, but I'm not going to make any promises just because the man works very long hours.
Yep. But
Do you have anything to say to any Tally Hall folks at the end? They've been so nice during this.
No, sure. I mean, I was going to say thanks for having me on. It's
Oh,
good
thank you.
to do it. It's kind of fun to do it in this format, and hopefully we were able to answer some questions. And I don't know. At some point we can plan to try to do a follow up and maybe.
I'd love it. I think other people would love it too.
Yeah, and I think this was a good time with the vaccine. Both of us being right around getting vaccinated, and I think the time a lot of people will be able to soon. So
yes, please take whatever is offered to you. I'm going to leave you on that note. There was a question of, which one did you get? I got Mrna. You're getting Mrna. I would have gotten the other ones.
All three approved in the U.S. are a good idea to take if you can.
Yes,
certainly. Yep.
Please, immediately, if not sooner.
As soon as you can.
Thank you so much, Ross. Enjoy your food. I hope it comes, or that you can reorder it and it doesn't take 10 years to arrive.
I think we'll be able to figure it out.
Okay, good.
Okay.
Tell your
Awesome.
wife hello.
I will.
Thanks, guys. Thank you so much for joining us. I'm going to save this. Bye.
Bye.